Welcome, everyone. My name is Casey Wang, and I'm a co-PI for the FABRIC project. Thank you all for joining us today for the sixth installment in our Mastering FABRIC Tips and Tricks webinar series led by Justas Balcas. Next slide, please. Before we begin, I'd like to just share a few housekeeping items. The webinar will include a live question and answer sessions following the presentation. Please note that the chat feature has been disabled, so if at any point you have a question, please go ahead and type it into the Q&A box at the bottom of your screen, and we will answer it during the Q&A session. Last, this webinar is being recorded, and we will be sharing that with all the registrants after the webinar. Next slide, please. We're joined today by our presenter, Justas Balcas. Justas is a software engineer at ESnet, specializing in software-defined networking and scalable infrastructures for scientific workflows through the SENSE project. With extensive experience at CERN and Caltech, he has managed Tier 2 scientific computing clusters, designed on-premises Kubernetes environments, and integrated advanced network services in distributed computing environments. His expertise spans grid computing, Kubernetes, and automation tools like Ansible and Puppet. Justas has contributed to global scientific collaborations, including CMS at the LHC project, and has co-authored publications on topics such as software-defined networking for exascale science and distributed data analysis systems. Now I will pass on to Justas to start the presentation.
Hi, everyone. Thank you, Casey, for kind introductions. I'm really happy to be here and present the work we do. So for today, I will cover kind of various aspects of SDN complexities, the SENSE project, software routing, and how FABRIC integrates together with these technologies. In summary, I will be covering a few topics. So first of all, just understanding the complexity of SDN layers in wide area network context, identifying some of the gaps in multi-domain, multi-resource infrastructure, introducing to you the SENSE project as one of the solutions, and also we'll cover the FABRIC. And in the end, I will do the real-world performance demo, which we're gonna do in live. So if I go to the next slide. So software-defined networking introduces programmability to the networking, but it also comes with complexity. So we have to deal with multiple domains, each having its own different policy, control options, or maybe different available services. We also have to deal with a variety of hardware and software vendors. We also have different APIs, orchestration tools, and also the controllers. And for the last mile connectivity issue, sites provide the different storage solutions, maybe different transfer tools, and also the expertise available at the site is also different. This heterogeneity makes it really difficult for us to achieve a seamless end-to-end networking across multiple domains. So the challenge is kind of clear. We need a way somehow to orchestrate all of these resources across multiple domains, while we also ensure the consistency, performance, and able to automate everything in one. So we need a system that works across different administrative domains. It can support dynamic resource allocation, and it provides performance guarantees, and it can also reduce the operational overhead. And also, we want to solve the last mile issue for the end users. So that's where SENSE project comes in. And it provides a solution for SDN WAN problem, while all the control pretty much remains for the administrative domain power. So SENSE, as name says, it is software-defined networking for end-to-end network science at the exascale, and it's designed to tackle the SDN challenges. what it enables us dynamic and high-performance networking by automating all of its resource provisioning via multiple network domains. It offers an intent-based API for users to discover, negotiate for networking resources, and also enables us the real-time monitoring and adjustments on the network. So SENSE operates through the resource managers, which are managed by the central SENSE orchestrator. What resource managers are doing, they are handling resource discovery and negotiation. The orchestrator ensures that the end-to-end lifecycle of the network service is always active. And for the intent-based API, it allows users to request the network services without requiring pretty much deep knowledge or network expertise over a wide area. One of our use cases is enabling Large Hadron Collider experiment like CMS and Atlas to perform smart data placement, enable network-aware data transfers, and automate prioritization of where data transfers while the network resources might be limited. In addition to that, we also provide the real-time monitoring data hop by hop and allowing them to identify the issues or, for example, test the new capabilities. This integration supports a high throughput workflows across multiple sites, which guarantees network performance. However, we have faced few challenges, which I will highlight, and FABRIC was one of the key elements for us to test the new capabilities. So the first challenge we encountered was the hardware diversity. We work in heterogeneous environment where we have to deal with different vendors like Dell, Arista, Sonic, or FreeRouter. We have different command line interfaces and also configuration management approaches on each of these devices. And there's also no standardized configuration between different platforms. With these issues, this kind of increases our maintenance efforts, and troubleshooting complexity over multiple domains becomes very hard. So first approach, which we took to tackle this problem, we started to use the Ansible collections from vendors. While Ansible community provides a great support, complexity increases as we add more and more devices. We have, for example, inconsistent naming parameters, which adds additional development, or you need more maintenance of different collections. For example, as shown in this diagram, each device requires different input for VLAN creation, and there's no same key and value parameters for different devices. For this to scale, we would need to support this in our code base and way to change configuration file based on a specific device. Additionally, the list of supported modules per device are huge inside the Ansible collections, and we usually have to rely on third-party solutions that can easily disrupt our production and operations. Using a big library covering many features is amazing, but for our use case, we mainly need layer 2, layer 3, and BGP control, so we need a very minimal set of Ansible collections. As you see in previous slide, inconsistency between configuration parameters makes implementation of end-to-end control much harder. And lastly, another challenge we faced as we started to use more and more devices was unsupported modules or collections by developers or Ansible community, mainly because of needed upgrades to the newer Python or specific improvements to the code. So at this point, we needed something well-maintained, open source solution for device manager, where we have decided to use as much as possible from Ansible, but also fork and build our own Ansible collections. So to address these challenges and simplifying the network management and add all the new devices, we leverage our own custom Ansible collections for different device types. We standardized configuration format where VLAN, BGP, or prefix list and route maps are expressed the same way for a different device. This did reduce our operational overhead and minimized errors when managing large-scale distributed networks, but it did increase our efforts on creating and maintaining our own Ansible collections. For example, if site or network resource manager wants to deploy a SiteRAM, from site's point of view, it only required to specify the network operating system type. What Sense Resource Manager will do, it will translate all of these requests mentioned in the previous slide in the correct device commands to create and provision network resources, either using CLI, RESTconf, or netconf, as configured in our own Ansible collections. As of today, we fully support 7 network devices and most features required for dynamic provisioning across multiple domains. We have built an Ansible collection for each of them, which takes the same input for the configuration, and Ansible behind the scenes translates all of these calls into the device-supported language. But the list keeps growing. As we keep expanding and adding more sites, we are required to support more and more devices. So right now, we are working on adding support for Mellanox, Dell OS 6, FreeRouter at those additional sites. However, not all features are universally supported. For example, on Dell OS 9 and Dell OS 10, it does not support VLAN translation. Some devices still require further development, like Cisco or Juniper, to support VLAN translation. And we also recently added a new feature for full end-to-end monitoring, allow users to issue a ping and trace route on a provisioned network path from a network device. This required us expanding the Ansible collection to support these operations, and I will cover one of the features which we added and how it was solved in our use case. So, for example, the ping feature has a standardized YAML file and format. However, as you can see, different devices use different commands to execute ping. So what Ansible allows us to do is to template these commands to ensure that we have compatibility across devices. Users in most cases communicate with Sense Orchestrator and do not have access to the resource managers or provide the following YAML configuration. And all of this is automatically done once real-time monitoring is requested, and I will showcase during the live demo. So once Ansible receives this request, for each device, we can template using Jinja all the necessary commands based on the YAML provided and issue ping command on a specific device using those parameters. So as we continue to grow and adding more and more devices, maintenance and development time for new features are increasing, and it can easily take from weeks to months to implement, fully test on many different vendors, all the new functionality we want to add. Additionally, we also have some deployment sites where we have no network control. To address this, we started exploring software routers and using FABRIC to test layer 2 and layer 3 provisioning and control this at the server level. Additionally, one of our interests is utilizing also the new technologies and also network overlays, like, for example, Kubernetes Calico VPP. So for this one, we built an Ansible collection, which currently communicates with FRR and VPP running on the FABRIC testbed. But you might ask, what exactly are the software routers, VPP, DPDK, and how all of these tools are working together? So just to give you an idea, DPDK is the data plate development kit, is a key component in software-based networking. It allows us to achieve high-speed packet processing. It bypasses the traditional kernel networking stack, and it utilizes the hardware acceleration features. If you want to reach 100 gigs or more, DPDK is the crucial component for that. VPP, as it stands as vector packet processing, enhances packet processing by providing a modular packet processing framework. It runs in a Linux user space and can be easily deployed on a bare metal, VM, or container. What VPP also offers, you can do a plugin-based architecture where you can load all the external plugins, or you can write even your own. It also supports a multi-language API bindings. So what VPP does, it can leverage DPDK to connect to physical NIC and offload some of the packet processing task onto the NIC. So we use VPP alongside with FRR software router for dynamic routing in our tests. FRR was our first choice to try out functionality and see how it works. And of course, there is also additional open source software routers available, and we plan to evaluate their performance in our setup and also provide an option for site admins to choose which one to use. And that's where Fabric plays a crucial role for us. We needed a test environment to evaluate VPP, DPDK, FRR, and test their performance before deploying them in real-world networks. What Fabric enables us, it's a cutting-edge experimentation and research at scale in areas of networking, distributed computing, and science application, and allows us to create rich topologies and test different tools, applications, while simulating how it will work in a real-world example. So for my demo part, you can find all the code base at the GitHub repo. And one of the things I always like to do, if there is an option to avoid any installation at the bare metal or VM, I always try to run everything inside the Docker container. So pretty much all the installations are based on the Docker container, and you can find them in the repo, and it avoids the host and VM level configuration changes. So it can easily be replicated on another site or another Fabric slice. So just to cover a few parts of installation, for VPP installation, the main requirement is to include the VPP repository and install VPP package itself as highlighted in bold. We do apply a few modifications, such as using the supervisor D to manage the process and adding also the monitoring script, which I will cover. So what VPP provides you, it provides you a real-time monitoring what happens at the VPP process. So for FRR router, there's no special configurations. We use an official FRR image and keep configuration very static, as most things will be controlled by the Sense Resource Manager, and Sense Resource Manager and Orchestrator will decide what rules to add into the router. As we began to work with VPP and control its behavior, we implemented some dynamic control via environment variables as VPP process starts. This allows us to choose how many cores do we want to allocate or how many buffers we want to use for VPP. Additionally, it also enables control over RX and TX queues for each device under VPP management. With this, we can see and identify what is the minimum requirement in terms of CPU memory for VPP to reach 100 gigabit or even go above and beyond that. So there are a few important caveats to remember once working with VPP. So what VPP requires is interfaces to be down before it can be used by VPP and DPDK. This can be easily handled by providing like a configuration file at the Docker startup. If interface is not down, VPP will not be able to start and use the interface for the offloading. The important thing is that VPP itself is only a data plane implementation, while FRR is to control the routers as on the Linux server. So at this point, we needed a way to exchange the routes between two different containers. So as VPP follows the plugin-based architecture, we can use two plugins. So one is a Linux control plane, which allows us to create a mirrored interfaces inside VPP, and the netlink. So the netlink synchronizes routing information from the Linux kernel into VPP. With this setup, FRR can continue adding routes to the host routing table, and VPP using the netlink plugin will import those routes into its own process. So what netlink does, it scans the route changes periodically, and it updates its process with a new routing table. As I mentioned about a small modification for VPP Docker container, VPP provides its built-in Prometheus exporter, which provides metrics about the whole VPP process, interfaces, buffers, misses, and errors. you can easily visualize this in Grafana dashboard and allows you to monitor the VPP performance in real time. So I will showcase some of these tests during the live demo. One simple test we tried is just to, let's issue simple ping. As you can see in bold, VPP's latency is over 80% lower compared to the kernel routing, and this looks kind of a huge improvement. And we also tested another one, just sending UDP flood traffic and sending large number of packets and measuring the delivery time of the UDP packet. The interesting result here is that VPP latency is 40% lower. It does exhibit the higher jitter. One possible reason we think that is because VPP processes packets in vectors and handles them as a graph. So it's processing 256 packets at the time and getting another range of vector. We are still investigating for the details to kind of confirm this theory. And of course, finally, we tested the network throughput using software router without VPP, as you can see on the right top, and also compared to the same setup using VPP, while also controlled by the same FRR router. The network path we used for this test was between CERN and San Diego. And as shown in results, you can see that with VPP, we can achieve very stable 100 gig flows, where standard software router running just on a Linux server fails to reach the similar performance. So to move forward, the full end-to-end LHC data transfer testing, we did encounter some missing features on Fabric. The Fabric team was very supportive and helped us providing all the certificates, DNS records, creating point-to-point link between Fabric router and our slice. So these things are currently configured manually, and we hope in the near future we could have those capabilities to be requested by the end user automatically, maybe during the slice creation. So with all these features in place, we can now deploy our solution on Fabric and can easily scale it to our production and testbed clusters. So what Sense gives us? It allows us to request network resources and paths through Fabric, Internet2, ESnet, JANT, and also our research and integration networks. One of our partners at UCSD operates a distributed Kubernetes cluster, and it's integrated with most of these network and research education networks. So what NRP is? NRP is a national research platform. It's a partnership between 75 institutions worldwide. It enables scientists and also network engineers to conduct cutting-edge research and test new capabilities. By integrating NRP with Fabric and also other network providers, we can evaluate the new software in a controlled environment and identify gaps or areas for improvement. NRP also provides many different SmartNICs and GPU resources distributed worldwide and allows us by joining these two testbeds together to test some innovative ideas. One of our first experiments using Fabric and NRP involved creating network loops across wide area network via multiple network domains. So what we wanted to study is the software capabilities and network behavior and how various constraints can affect the performance for the real data transfer. One key requirement for the high-luminosity LHC experiment is to sustain 400 gigabits throughput per site. So our goal was to identify what are the network configurations needed to achieve 400 gigabit. What is the impact of the jumbo frames on the throughput? And what is the minimum CPU and memory requirement to sustain 100 gigs, 200 or above speeds? So we presented those results at CHEP in last October, and the full publication should be available by summer. One of the key findings was that the transfer application in use has the bottlenecks, preventing us from exceeding 250 gigabits on a single server, even when running multiple processes. We also tried to connect back to two servers. We reached pretty much the same performance. So if we have no limitation in the storage layer and we have multiple servers, we can conclude that with just 2 servers, we can achieve above 400 gigabit over long distance going from California to CERN at Switzerland. So for today's demo, I will be using the facility port feature, which was presented by Tom and Benjamin in FABRIC webinar on November 25. And one addition since then is that the NRP has also deployed a node at CERN, which has a direct connection to the FABRIC facility port. And we will utilize it to connect to NRP node, also to our VPP instance, and also creating a connections going from CERN to San Diego in California. So I will walk through full deployment of FRR, how we can deploy VPP, and demonstrate how to request network paths via Sense. We're going to request multiple paths dynamically, and none of these paths are pre-created in advance. So one of the paths I will do is the yellow path, which will go from CERN to San Diego and will traverse multiple domains like FABRIC and ESnet. And the green path will use FABRIC slice VPP to establish BGP pairing between FABRIC slice, which I have, and also the SDSC router. Additionally, we will connect the CERN NRP node and provide to the NRP node the FABRIC public IP address on our slice running at CERN. So before jumping to the demo, I would like to acknowledge many individuals who contributed to the development, operations, and improvements of this end-to-end SDN WAN solutions, and it's a joint effort by all of these people working towards the same goal. So here are some useful links where you can learn more about our work. Additionally, if you are attending OFC or FABRIC 10, we plan to showcase our demos, which I highlighted in today's presentation. And just to highlight, FABRIC workshop will be on March 11-12, and we have also submitted a demo request in which we will showcase today's demo, but also expanding it and showing more detailed X3D deployment and transferring the real LHC data via FABRIC and other network domains. Okay, now it's demo time, and for demo, I will do 5 things. So the first thing, we will go and deploy the software router, FRR, just issue some pings and see how it works between FABRIC slice. After that, we will redeploy everything with software router, FRR, but also we're going to deploy together with VPP. And once we have this set up, we're going to use Sense to create multiple network paths. One path will go from NRP CERN node to NRP at SDSC. Another one will go from NRP CERN to FABRIC VPP, and also the last one will create all BGP peering, and we can do this ping and network test on the FABRIC. Okay, let me switch screens. I hope you can see my screen. So here is my FABRIC slice, which is available on GitHub repo. So on my FABRIC slice, I'm just importing some Python libraries, configuring FABRIC. Also, for the configuration, we already started deployment on multiple sites. So we have at CERN, Los Angeles, New York, and UCSD, where we also have to configure our own private ASN numbers. I already have this slice, so I will not create slice because it will take longer time to do that. And on each of the sites, we have one specific IP range, which we have allocated for our testing. So if I go down, I do have some configuration parameters to some functions to run the command on the FABRIC node or do the interface tuning, which I will cover, and all, for example, run the local command on my slice. So creating the slice, CERN node is a bit special. So on the CERN node, we are using 2 dedicated NICs, not 1 NIC. So what we are trying to achieve, let's say we have 2 dedicated NICs, can we reach 400 gigs or using all 4 interfaces on the same NICs? So that's one of the features we are trying to test right now. Deploying monitoring, it's quick and easy. All the node tuning and high throughput. So mainly what I'm doing is just installing the Docker, and everything else is inside of the Docker containers. If I look on the VPP FRR tuning, one of the tunings which we apply is pretty much the sysctl tuning. So we increase the memory, all the tunings for the high throughput network, so that we can reach 100 gigs and more. And this one is configuring IPs on the host, creating routing tables, and now that's where I come. So I do have FRR already running, there is nothing on it. So no Docker container running, there is no network configured on it. It's only pretty much plain basic container, VM. So the first thing what it will do, it will deploy the FRR and configure FRR to be a router, but in that case, we are not using DPDK. So what it will do, it will configure all the interfaces, it will add all the IP addresses, it will disable accept array, because we don't want to have route advertisements happening. And once this is up, it will also, we will move to deploying FRR, which will start through the Docker container. So as I mentioned, there's no big changes. The only thing what we are replacing is the host name and ASN based on the site, and all the FRR configuration remains the same. Let's take a look, it's still going. So for this one on the FRR VM, I do have 4 networks. So I have VLAN 99, which I'm using for the accessing anything outside. And I have a layer 2 connectivity, and between all the Fabric VMs, VLAN 100, 101, and 102, where I've set Fabric IPs, but we are not added into anything routable outside. Okay, so this one finished, we can deploy FRR. One thing what we are adding is the SSH key. So the resource manager running at Sense uses SSH key for this specific deployment to access the device. So that's how it's communicating. So it SSH to the node and communicates using FRR or VPP commands. So now it deployed, we can check that we have FRR running. So, and it is running. So one thing what I want to do is from the host 2, where we have, and I want to simply do a simple ping to the FRR router. So I can see that I can ping the FRR router. At the same time, I can ping another node, which is a host 1. So I can ping also the host 1. As you can see, the time is like 1.4, 1.3 milliseconds. So moving forward, I want to move more on the VPP. There's additional step which we do is adding the default route. So what this does is, because if we want Sense to be able to communicate, we need to instruct the node from which route or which network you can access to the outside, or how you can communicate with the outside of the network. We're going to skip that, and we will proceed with deploying FRR and VPP and configure FRR to be our router. But in that case, we are using DPDK with VPP. So this one will stop the all the containers. It will set all the interfaces down. It will delete all the interfaces, because that's the item which I mentioned. But for VPP to be able to start, it requires all the interfaces to be down. And so it's deleting all the interfaces. Okay. Now we can proceed deploying VPP. So there are a few scripts which we are using in addition to that. There is update CPUs and find interfaces. If we go to VPP repository, find interfaces, it's mainly getting the interface name and it's identifying the PCI device name. So for VPP, you also need to specify a specific PCI number inside the configuration. And for update CPUs, so usually for VPP, you have to specify what is the main core for the control and also which CPUs to use for VPP process itself, communicating with the NIC. And it's also updating everything inside the environment variables, which is mounted inside the container during the startup. So all of these parameters are modified during your startup, and you can easily change them based on your needs. So if we go back, yeah, so in addition to that, it does create the Docker container from scratch. So it's always recreating the new Docker container. Now, if we look here, we already have VPP running. I can do docker exec -it VPP and I can say, show me interfaces. I can see that it did create all the interfaces, 100, 101, 102, which are inside VPP. And we also have configuration for high MTU on those interfaces. Now, if you look on the host, you will see that now interfaces named the same way as named inside VPP. So it is E1 and E2 and E3 and E4. And you can see also it has an IP addresses on those specific interfaces. Now we can deploy the FRR router, which is pretty much the same what we deployed previously. So the only thing what we change is deploying VPP. So there's nothing else to configure on the FRR router itself. It will identify all the interfaces, all the routing table, and it will see what's really happening on the node. Okay. Oh, did I click it again? Oh, sorry. So I redeployed VPP again. That's okay. So now it's deploying the FRR router. Now, at this step, we also need to execute the routing tables and tell that if you want to communicate with outside, because the resource manager running for this specific slice is running on NRP Kubernetes cluster. So for it to SSH, we adding the routings into the route table that any range which we have defined. Let me go up here. So we know Fabric range, CERN range, or Fermilab, Caltech, and so on, that they can access the Fabric slice using SSH, so that we know where to go to access this. Okay. And option 2. Okay, this one was deployed. Okay, let's go back to our instance. So now we can see that we have VPP and FRR running. If I issue the same ping, you can see that if I'm pinging the router, I already see like twice lower RTT. Now, if I issue the same ping to another node, you can see that there's difference already, like factor of 3 or 4. So it was 1.3 and now it's 0.36. Now, all is nice. What I want to do is now I want to start using SENSE and provision some network paths. So for this one, I will go to the SENSE orchestrator where I want to create a network path going from NRP node and go to NRP node at ECSD. So what you can see on Sense graphical interface, you can see all the sites which we are controlling right now, all the DTNs available for sense control. So there is an ultralight, there is also NRP Nautilus, another Nautilus production. We also have Max, UNL, Thermalab, and so on. So for this one, I do have few examples ready. So if I go here, NRP CERN to NRP SDSC. So this one request is saying I want to create a 1 gig pipe. I want to assign IPv6 addresses on both sides, and I want to do it from a specific UCSD NRP node and also go to a specific, this one is at CERN, based on the host name, and I want to go to the SDSC on a specific interface. At the same time, what I'm telling it, I also want to traverse the ESnet network. So because there is a direct connection at UCSD with Fabric, so it will choose the shorter path. So in that case, I'm saying you should go through ESnet so that I want to have a longer path. And of course it failed. And we have to do debugging. That's always like that during live demos. So one of the reasons I think I already know, because I'm doing this in live and there was nothing deployed, there is a timing, how long does it take for Sense Orchestrator to find out about the resources and that the Fabric slice control is available. Let me do quickly restart one of them. Okay. While it restarts, I can jump and request another resource. So we can do Fabric SDSC, NRP SDSC FRR. Yes. SDSC FRR. Let me check if container is already up. Okay, it's taking a bit of time to start the container. So let's check if we have the full path. I mean, there's also an API where you can easily check and ask and negotiate. I did not prepare for this one, but we can do this live and see if everything is ready. So we do have Fabric and ESnet, and also we have the CERN Fabric FRR connected. Okay. Let me try again. Okay, let's move to another one. In that case, something has failed and I was not prepared for that. So we can request NRP CERN to VPP Fabric, which does go from CERN Fabric FRR to the NRP node at CERN. Okay, so live demo is not going. Something has failed. I do have some backup on the slides, which I can jump in. Let me do quickly. So I guess I will have to record this in addition to that, and I can show you later. I need to debug what really failed. So for that specific request, what you can get is you get a path request going from NRP at CERN, and you can get all the topology information, how things are connected. At the same time, is whenever you're requesting only between CERN and FABRIC VPP, you will get only jumping through the FABRIC node, FABRIC switch, and between two hosts. And in this case, you can do a BGP peering, stitching another one service on top of that. And in that case, it will show you the full topology on how things are connected. So in that case, I can easily request a BGP peering between SDSC, CERN, or any other site, which we have a full control. I think I will have to stop here, and if you have any questions, I'm happy to answer them.
Thank you, Justas. Then we'll now move into the Q&A session. We'll begin with some questions that submitted during the presentation, and we'll get started. The first question, how is the experiment set up on Fabric? Do you have to create the network circuits in advance?
So the only thing which is configured is the Fabric slice itself, and all the network circuits are not configured in advance. That's what I tried to do live, but there was some failure. It might be that a specific resource manager is currently not available, and it's telling me that you are not able to create a network path. So none of the circuits were created in advance.
Thank you. The second question, regarding the 100 gigabit flows, are those single stream TCP flows or some other packet transfer?
Those are not the single TCP stream flows. It was mainly, if I'm not mistaken, it was 200 flows happening between two servers and traversing through the loop. So it's like 200 flows at the same time.
Okay. The third question, in your experiment, you use dedicated NICs on VPP. Is it possible to use NIC basic for running DPDK and VPP applications?
Yes, you can use NIC basic and to run with DPDK and VPP, but in that case, the performance will go down because you're not getting the whole NIC, you're getting only a fraction of the NIC. So what we see in the performance is around 25, 30 gigabits per second.
That's good. The fourth question, would it make sense to run VPP in a DTN, not for routing, but just to increase its throughput?
Based on what I've seen, yes, and especially if you look on the, for example, Kubernetes and Calico VPP, there is implementation to increase the throughput at the host level, just using Calico and VPP. So yes.
That's great. Next question. How do you plan to integrate HPC job schedulers like Slurm or Flux or container orchestration platforms so that network and compute reservations are co-scheduled in a super facility model?
So there is an ongoing effort right now looking into that. For now, we are mainly focusing on the data transfers, which means on the super facilities, you have a Globus endpoint. So it's between two Globus endpoints. In the near future, I hope in a 6 or 1 year, we plan to look into the Slurm, HT Condor, Flux, and how we can integrate that and request the network services going directly to the DTN itself or the job runner.
Thank you. The next question, to be able to run experiments at 100 gig or 200 gig, do you need any special software or special configuration?
So the only configurations what we change is MTU and TXQ length, MTU 9K, TXQ length 10K, and all the sysctl tunings, which you can find on ESnet's page. In terms of hardware, no. We use just same ConnectX-7, which is 400 gig capable, and of course you need to have 400 gig gear to be available. So there's no special. We use the same what is used during normal days.
Thank you. The next question. How do you see SENSE's ontology-based approach fitting with broader network orchestration standards like ONF, TOPI, IETF, TEAS? Is there a roadmap to achieve widespread adoption across other RNE networks?
So I'm not very familiar with this ONF, TOPI, and EITFs. I would be happy to read it and give an answer later. And for widespread adoption across our research and education networks, we currently support like 22 research and education networks. So it's covering InternetChew, ESnet, JANT, Europe, US, and Asia. And we are slowly progressing and also adding our research and education networks.
Thank you. The next question. When you're using the TerraCore, were you able to use up the whole 400 gig bandwidth?
Yes. So for that one, for all the loops which we created, so we tested the small loops and the big loops. We used the ETHR, FDT, and the iPerf, and we were able to reach 400 gigs. The problem came when we started to use the real data transfer tool, and we were not able to reach more than 250 gigabits per second.
All right, great. I think we have our last question here. How can I get started and who can use SENSE?
I would say pretty much anyone research and education community can use SENSE, and we're always happy to discuss. And if you have a use case where you need network guarantees or network control, just get in touch.
All right, that's great. Thank you very much. And thanks again to our speaker, Justas Balcas. In addition to our presenter, we'll also like to acknowledge there's a team of behind the scenes members listed here who work diligently together to bring the webinar to production. We see Chelsea Davis, Jay Sri Jagannath, they're all on the FABRIC project. And next slide, please. Thank you to the audience for your participation in the webinar today. Like I said, in addition to a recording of the webinar, we will also email everyone who has registered with a list of resources. This slide deck particularly will be shared, and there should be a link to our Slack channel and a form, a Connect With Us form, where you can connect with the FABRIC team and to get more information. We hope that you will reach out to the FABRIC team for any questions or support going forward. Next month, our webinar will be Stitching Together Innovation with FABRIC Users on March 18 at 3 p.m. Eastern Time. The webinar will be focused toward new users, so we would appreciate it if you could forward this information to any relevant users in your communities that might find this interesting. And as a final reminder, for those who are already using FABRIC, please submit your FABRIC matrix and make sure your project abstract in the portal is up to date, because we will be using that information for outreach, promotion, including showing that on our website. So thanks again, and please have a wonderful day, everyone.